be thermal deformation in a rail string track structure. There will be no longitudinal thermal deformation in a rail body or in a rail head or in a string, as the length remains unchanged in summer and in winter. Neither rail nor string will have any thermal deformation joints along the whole length, similar to telephone wires or power transmission lines that are like strings in a rail fixed to supports with a sag and stretch without any joints for many kilometers. However, temperature changed in the structure can cause change in its stress-strain state. Skyway track structure is designed so that at any estimated temperature variation the rail and string are exposed only to tensile force. Therefore, the structure cannot lose stability, which could happen if these components were exposed to compression stress. For example, at maximal temperature difference of 100 degrees Celsius from plus 60 degrees Celsius in summer in the sun to minus 40 degrees Celsius in winter, the maximal range of tensile stress variations in steel rail string components will be about 2004 kg of force per square centimeter. For a string from 7,600 kg of force per square centimeter in summer to 10,000 kg of force per square centimeter in winter. For rail body and rail head from 0 to 2,400 kg of force per square centimeter respectively. With a reduced temperature difference, a strain-stress state will be proportionally reduced. Wheel temperature variations of string tension result in track deflection. With temperature variations, there can be observed track deflection in a string sag plane, which will be proportional to its initial sag and relative tension variation. At temperature variation of 100 degrees Celsius or a more neutral value of 50 degrees Celsius, maximum vertical track deflection at a 30 meters span will make about 2 millimeters. In this case, the track will have a 2 millimeters upward deflection in winter and the same 2 millimeters downward deflection in summer. Such micro roughness is easily compensated by a wheel suspension and will not affect the smooth motion of unibus moving at speeds of up to 500 km per hour. Furthermore, as thermal deflections have a predesigned and known in advance character, at this air temperature, the track profile will be automatically adjusted by a computer-controlled wheel suspension, if necessary. In addition, there are design and technological know-how which will exclude track deflection at temperature variations. Will the rolling stock change string tension when in motion? It will, but not much, just within 1%. It is explained by peculiarities of kinematic scheme for the rail string track structure. Figure 17 shows a string block system, string tension in which does not depend on external load P but rather on tensile force T only. Such structure can be transformed into a linear scheme of a greater length. The analysis showed that at P less than 200th T, which is observed in Skyway, the strain-stress state of structures shown in figure 17 and 18 differ from each other by not more than 1%. In engineering estimates, this difference can be neglected and structures can be considered identical. This considerably distinguishes Skyway from other building structures, for example, bridges and overpasses. The latter are exposed to millions of loading cycles in the course of the operation, and each time the stress in various structural components, for example reinforced beams, increases by 2 and more times. All this results in the development of fatigue phenomena in the structure and therefore reduced service life of structures and growing maintenance and repair costs. As Skyway's train stress state remains practically unchanged during the whole period of its operation, irrespective of the number of loads, such train rail track structure will have increased total durability. How accurately are track range perimeters observed? Left and right train rails will be linked with each other every from 10 to 20 meters with special cross bulkheads that fix a range like sleepers of a railway. The side force in the interval between them, for example, under the impact of a hurricane, side wind of from 100 to 150 kg force per one wheel will change the gauge width by from 1 to 2 mm as a result of rail strain deflection, which will not pose any danger to the unibus rolling wheel moving at speeds of up to 500 km per hour. What will happen to a rail vehicle if rails slide apart? This risk exists at railways, including high-speed railways, where numerous train derailments happen due to this reason. It happens because the train wheel has one flange. In a Skyway module, each unibus wheel has two flanges, by one flange on the left and right side of the railhead, see Figure 19, and an independent suspension. Therefore, a rail vehicle will not be critical to the gauge width. For example, a wheel suspension can be designed in such a way that variation of gauge width by 10 mm will not result in derailment, but rather will be a regular operation mode. In the light of the above, coming off the track is more typical of cars that are kept on road surface only by friction force and often fall down to the side ditch, especially under icy conditions, whereas the rims available on a wheel pair of trains keep them stable on a track. Moreover, rail vehicles are equipped with an additional anti-derailment system side rollers, which bear against said rolling surface of a rail. Therefore, they will also maintain the design gauge width.